Okay, this is, as you're all aware, as part of a PhD. This isn't a thesis defense, this is proposal defense. Ideally, this is done within 2 years of starting your PhD, but they're pretty routine to be a little bit longer. This is about 3.5 years. But the purpose of this is for the committee to make sure that they feel what is being proposed is a suitable topic for a PhD and not too much either. It's also an opportunity to make for a candidate to say, you know, you can't ask me to do too much. And so what Brandon's going to be explaining is what he proposes to do. Of course, 3.5 years in, much of it he's actually already done. That's the reality of it. And I mean, I'm the supervisor, but Brian and Giuseppe have been on the committee for quite a while, and Ian Church from University of New Brunswick, he will be the external, and I was surprised. The ocean engineering actually like to have the external weigh in on the proposal stage, just to make sure, again, that the topic is reasonable. So at that point, I'll hand over to Brandon. I think most of you know him. He's been here a lot.
Yeah.
And so I'll let him talk about his topic, and we'll assess the feasibility of the proposal.
Well, thanks for the introduction, John. I maybe don't have the most typical path through the PhD here, but nonetheless, we've reached this proposal stage. And a lot of you guys have seen this story before. This is working. So we've got bathymetry, right? And we obviously see these sort of artifacts in the data. Now, I've been looking at this for a long time here. And what we're going to try to do is actually remove these artifacts, so parametrically estimate them, and do so in an efficient, robust manner, so that we can go towards having a real-time implementation of this calibration routine. And that's because some of these sources of errors can change through time, and if that is the case, we want to be able to track in on them pretty quickly. So this is what you typically get from a sonar system. You have a swath of data, and you got some really nice geomorphology going on, but hindering your analysis of it are these artifacts. And what's happening more and more now is you have automated classification routines that use the structure of this surface to segment these regions in bathymetry. And these artifacts are going to kind of just obscure these routines. So we want to remove them in an effort towards a perfect data set. Of course, this is, you know, a dream, a lofty dream, but we can go towards that path at least. So what you could do is hide the wobbles. This is a sun-illuminated surface. So because you can choose the direction of where the sun is coming in from, if you go parallel to all those wobbles, they seem to disappear. But what I'll show you is that these follow the ship around, so you can't really remove it for a whole data set doing something like this. And we don't want to hide the errors, we want to get rid of them, right? So this is the setup, the system setup that acquires these data. This is just one swath, as I mentioned. The ship's going along here in what we call mowing the lawn. This is one line. And we have a system that sends out a ping, a pulse of sound into the water, and we can subsample that pulse multiple times across track, and we can sort of paint the seafloor in a high resolution. So multi-beam systems are very good at just seeing what's happening at the seafloor. Now, these systems are implemented by much of the Office of Coastal Survey's fleet. They have motherships, launches. These all utilize Kongsberg triple sector systems, which have a long track stabilization to get a nice consistent distribution of soundings on the seafloor. And what should be mentioned is that along with these launches now, what's becoming more and more common are the autonomous surface vehicles. So these are even smaller than these launches, and what we've seen is that it's actually the vessel motion that creates these artifacts. And because these launches are even smaller, they're more susceptible to motion, so more artifacts. So it's just homing in that we do need to remove these errors from our systems because they don't really seem to be going away. We're not developing different modes of acquiring data. So this is the stabilization that I mentioned that occurs. And I've created simulations to recreate this and study this sort of problem, and I have modeled this as well. So you'll see that popping up a lot. But the thing I want to drive home here is the subtleness of these errors. So you do have some geomorphology. This isn't a seamount, this is just some bedrock. And overprinted are errors in the system, so systematic errors that are a percent of water depth, maybe less. And the wavelength of them, I'm going to get more into that, but it is essentially a scaling, a product of your vessel speed and the vessel oscillation, which is driven by the wave period. So to remove those errors, the first thing we have to do is find out how do these errors propagate, these systematic errors propagate to the seafloor. So what we did here was developed a mathematical model which represented all the inputs of the system to finally get that X on the seafloor. So that's the remote position. So what we start off with is a sonar system, a transmitter and an array, a receiver array, and these send out pulses into the ocean in a beam pattern, and we can model that beam pattern, at least the more responsive part of the axis, as a cone. And what we're going to want to do now to figure out where does the sound go in between these cones is to orient them in space and position them in space. So the first thing that we do is put on a motion sensor. So we have a roll pitch sensor and a gyro for our heading, and these combine to at least let us orient them in three-dimensional space, so we kind of know where they're oriented. Then we also have to position them. So all these vessels have a GNSS antenna on the top of the vessel, and with that combination, we have a three-dimensional georeference of these cones. Now, what we don't know is where on these cones, so we know where we steer these cones to, we measure that, right? That's just an array problem. But where along these cones, which azimuth did the sound that we heard come in from and exit along that cone? Because that's part of the geometry that we're going to need to solve to be able to actually position that remote sounding. So we can guess it fairly well with some methods, but to really home in on the exact location of intersection, what we do is project those cones to the remote seafloor, and then we have a conic section, which is a hyperbola. And we can then intersect these two hyperbolas and find out exactly where did that sound hit the seafloor. Now, this is a numerical approach. Intersecting hyperbolas is not closed form. So the currently published method intersects these hyperbolas in this plane here, and then to constrain the measurements to the measured two-way travel time, so we measure the time between transmission and reception, you then adjust this vertical or focal plane, is what it's called. So what we end up seeing, though, is not that flat seafloor. We have some sort of wobbles in the data. We have oscillations. And we want to know what is causing these exactly. What part of this model is actually the source of this systematic error that's propagating to the seafloor. Now, John here in the room found out that these wobbles occur with the wave period. So they're corresponding with the actual motion of the vessel here. And because you have these 6 sources of potential unknowns or errors in the system, so your X lever arm or your Y lever arm, or a latency between the motion sensor and the multibeam, as well as a heading misalignment between the roll pitch sensor and the multibeam, or a surface sound speed bias, these end up having a dynamic propagation to the seafloor. So you think you know where the multibeam is, you put this into your integration model, but you have an offset of where the array really is in space, and as the vessel itself moves, the magnitude of this error also moves. So it's a dynamic error that we're seeing here. And these are still fairly common because some people might put in a negative sign instead of a positive sign when you're setting up these multi-beams for lever arms. And latencies, we're doing better at correcting for latency between the pause sensor, for example, and the array, but there still seems to be sometimes some sort of latency left in the data. Motion scaling, that's more of a historic error. As systems degraded through time, the voltage output would also degrade, so where you think you are, so your roll value would just be scaled. And that heading misalignment. This is a subtle difference between the heading of the gyro itself and the array. That's corrected for by the patch test. But what the patch test doesn't correct for is the actual INF, the IMU, which is the roll pitch sensor and the alignment with that and the array. So surface sound speed error, that can be for a variety of reasons. You can have a miscalibrated sensor at the array head, or you can quickly go from freshwater to saltwater regions. And because we use a time averaged value for surface sound speed, at these interfaces, we do see a bit of an error. So these are 6 sources of errors that are fairly common in systems. They're still around, and we're going to try to remove all of them. This is how they get brought in to the model. So your lever arms go into your GNSS combination and tell you where the array location is. The other scaling, latency, heading misalignment, these go into your array orientation components. And the surface sound speed measure, this tells you where you steered that angle, that cone to. So you think you steered it here, but you may actually have steered it in a slightly different direction. And the way that these combine into this model is nonlinear. So what ends up happening is we actually have to optimize in an iterative routine. And this adds computational expense to the method, and this compounds upon the hyperbolic intersection that I showed you earlier, which is also numerical. So to optimize this system, what we've noticed is it does take a lot of computational power. So this is why a lot of the talk you'll see today is discussing efficiency and how we can make it faster. Next. So we have a mathematical model. We have a bunch of residuals. Well, we have a bad surface. Now we need to estimate these residuals, the true values, to then optimize it, right? And the way that we do that is we have a whole bunch of beams. So as I mentioned before, each ping gives you a whole bunch of beams across track. This is a combination of multiple pings. So this is a couple thousand beams here. We have multiple measurements. And we can utilize each of these to do an optimization scheme. This is a little bit different from what John commented a couple decades ago, where he looked at the individual pings. So he optimized each ping. But because I optimize individual beams, this method extends to deep water conditions. So I could optimize, in theory, not just shallow water conditions where the error is constant for a particular ping, but in deep water conditions where the error actually evolves during the ping cycle. So we have a whole bunch of depth errors which we want to estimate. So we're going to do that with a quadratic polynomial. This is essentially smoothing the surface and giving us a constraint. So we don't want to really use other reference surfaces because other reference surfaces can have their own integration errors, and then we end up kind of chasing our tail and estimating the integration errors in the other data set while we're trying to estimate ours. So in order to circumvent that and the fact that a lot of the time we're surveying where there is no reference surface, we use the data itself that we acquire and calculate a smooth version of it as our constraint surface. And that's what this quadratic polynomial is doing. So we have estimates of these errors, residuals. Now we want to actually optimize the system. So what you have typically is a sum of squares. So this is just showing you on the y-axis the cost or the sum of squares. And on the x-axis, this is your position in parameter space. So this is a y-lever arm error. We're currently here in parameter space, which is not the minimum, because the minimum would correspond with a calibrated system. And what we want to do is find out where that minimum is in parameter space. So you have a y-lever arm error of 1 meter error. You want to get it down to 0. This is a numerical approach to get to that direction. So we calculate gradients based on this mathematical model to then tell us where is the downhill direction in parameter space. So we can figure out at this point a gradient, but you see it doesn't actually follow the exact path. The exact path would be that nice curve, but we linearize it, we take a step, and because it's a nonlinear model, it takes a couple iterations to get there. So we take one step, we kind of go in a little bit past the true solution, but we kind of tack around the solution going downhill, and if all the assumptions of the model are held, we do get down to the bottom of that function. And that's the calibrated system. So what we're going to try to do is recreate this in field data. Right? Now, that was one dimension. We're working in 6 because we have 6 parameters, but the method does expand to higher dimensional space. So this is the same parabola, cost function in 2 dimensions. We've now added latency in the other axis. So the thing is, your tangent now is a plane instead of a line. Your gradient is a 2-dimensional vector, but you still go downhill in the same manner. and you get to the bottom there. I couldn't show a 6-dimensional parabola here for obvious reasons, but again, the method goes from 1, 2 to n-dimensional space. So for my master's, eons ago, I actually implemented this on simulated data, and we use it on an entire swath. So here's that quadratic surface. So we estimate it locally, and we don't do it on the whole data set because we recognize with a little foresight that the quadratic surface doesn't represent seafloor everywhere. But in some places it should. So what we want to do is do these local analyses and kind of move it through the data set. And what I was able to show with significant motion, we did test various combinations of motion, which some were better than others. And depending on seafloor fit, we got better estimates and times. And once more of your data is good, so once more of your seafloor is smooth than rough, and once more of your data has motion than not, you should have conditions where you can asymptotically converge towards the true calibration parameters. So I forced a whole bunch of known errors in here, and what you're seeing here, the forced errors in red, and local estimates are these dots, and we take a running mean. So as we get more and more estimates, we take the average of those estimates to get our calibration parameters, and we slowly do converge on the true data. Now this is just a small subset of data, but because it doesn't require interesting geometry like patch tests, we don't need to look exactly where lines are overlapping. We can look at a lot of data, and it allows sort of an asymptotic convergence of parameters, kind of leveraging the law of large numbers sort of thing. Now, when I went to field data, this is what the bathymetry actually looked like. Not those nice green flat surfaces that I was using in my master's, but we've got some geology here, we've got bedrock, we've got all sorts of relief. And I'm not knocking geology, but it just, it's not good for risk, right? It doesn't work very well in my model. So what I wanted to do was, we updated the thesis, did that already. What I wanted to do is look closer at these lines. So I created an entire framework in my master's to look at data and kind of debug what's going on with it. Now, what happened here is these lines are just distributed in space oddly, but what I wanted to do was kind of put it back into that framework that I had developed for risk. So I removed the trajectory of the actual line and kind of stretch it out, thanks, and stretch it out in space and remove the heading as well. So that kind of yawing that happens when you're steering the vessel, taking that out of the equation. So what we have now is just the wobbles going in one dimension along track, and we can now create a correspondence in space and time. So this is the motion of the vessel. You have roll, pitch, heading, and heave. And you now can see where these packets of energy correspond to the seafloor. And over here, there's not a whole lot of roll, there's not a whole lot of wobble. Here you got a lot of roll, you got a lot of wobble, but you also have seafloor. So we're gonna figure out how can we make an efficient estimation routine given this sort of data. Now, I ran risk through this whole window, and these are the 6 parameter estimates at the bottom. Don't really worry right now about the quantitative measures. Don't look at the actual values here. What I want you to get from this is a qualitative idea of how the data responds to the environment. So here, with the seafloor is nice and smooth, we've got nice stable estimates. You hit a little bit of bedrock there, you got a little jump. You hit a lot of bedrock there, you got a lot of variation in estimates, right? The whole time, this is a very good survey day for me. There's a lot of roll here. People on board were not too happy, a little seasick, lunch was skipped, but it was pretty good for analysis in kind of figuring out how is the seafloor affecting the method versus how is the motion affecting the method. So we want to clearly ignore these areas from the analysis, right? If we're trying to statistically converge on a solution, this is not helping us. These look fairly stable. You can imagine that the true mean is probably somewhere within this region, but this is just wasting computational power. It's not helping the analysis. It's not giving us a more confident solution. So because the assumptions are breaking down within this region, we developed a way to automatically detect these regions and remove them from the analysis. So here's another set of seafloor, right? You've got some interesting long wavelength sound waves here at the very beginning. Further on, you've got some higher frequency sound waves, and then some nice smooth seafloor, right? This could be a quadratic, maybe not perfect, but there's a potential for risks to work really well in there. And then at the end here, you got a little bit of bedrock. So these are areas that we would ideally like to find, remove from the analysis. So because risk is a windowed approach, just looking at local segments, we can extrapolate that framework to essentially just look at the seafloor itself, not actually calibrate, but just do a quick seafloor analysis where we can extract those depths, fit our quadratic surface through them, look at the residuals, and then based on how large those residuals are relative to some threshold that we set, we can then reject or accept the surface. So I could run this through the entire line in automated fashion fairly quickly, and I actually let the data determine what that threshold is. So depending on how smooth your seafloor is, it automatically expands or contracts the threshold to find essentially the best regions within that data set. And you can see that it is quickly picking up these bad regions, and I do accept the nice smooth seafloors. And I said we can do the same thing with motion. Very simply look at variance, again, within these windows, because we don't want areas where there isn't a whole lot of motion because there's not a whole lot of wobble. It doesn't make sense trying to extract a signal in those areas. So just looking at the variance of roll and pitch, because those are the main drivers of wobble, we can run it through again and we find good regions, bad regions, and what we want to really feed into the number cruncher is the combination of those. So you want nice green circles with green pluses. That means good motion, good seafloor. And anything with a square, a red square, say bad seafloor, or a red cross with a bad motion, outright rejection. So applying that to this data set here, we can see that we quickly and effectively automatically identify this bad seafloor. Pretty much all is good motion. As I mentioned, it was a wavy day. So it throughout these sections, which is essentially what I was hoping for, I kind of missed this one. There is a little bit of roughness in there, but it wasn't automatically detected. But the majority of the bad areas, bad for risk, again, nothing against geology, was detected. But the thing is, what I kind of want to propose here is instead of just using a quadratic surface, maybe we can use a better trend, right? I'm trying to smooth the data essentially and isolate the wobble. This is wobble from the underlying seafloor. So I went back into my simulator, and this is just a flat seafloor. Again, that nice green surface, but for this time it's grayscale. But you've got some oscillations here. This is the plan view looking from above, the side view. So you got those crazy wobbles. Now, again, this is corresponding with motion, right? So the vessel is rolling, the seafloor is rolling, corresponding together. But I don't want to just do a low-pass filter anymore. I don't want to just do a quadratic. What we're noticing is we're having these sort of spurious features, these high-frequency undulations in the seafloor that kind of pop up. And this is just what I did, is I put a Gaussian spike in there. So high-frequency pulse in the seafloor, and then I threw that oscillating sinusoid on top of it. So we've got low frequency and high frequency. Now a quadratic trend is going to fit this low frequency pretty well, but it's going to ignore that high frequency. That's going to leak into our analysis. So I want to kind of do something that does it all. It's a lofty goal, but in this condition, it would likely work fairly well because everything is in a straight line. So what we can do is just look at, say, a Fourier transform of the seafloor along this direction, for example. And when you do look at that one-dimensional, so here are the actual spectrums. The bottom is the seafloor, the top is the motion. Because remember, as I mentioned earlier, there's a correspondence now between space and time by stretching out this bathymetry, right? Now what you notice is that high power, low frequency, large wavelength signal does propagate. So this is that long wavelength, 400 meter oscillation that's in there. But if you zoom in on the high frequencies, what we see is at the periodicity of the motion, we also can see the periodicity of the wobbles. And this was fairly interesting to me because what was happening in these wobbles is it's not exactly a consistent sinusoid. You've got this weird out of phase oscillation occurring, but nonetheless, we're able to pick it up in the spectrum. And the reason for that is because I'm looking at a two-dimensional spectrum. So what ends up happening is on the left you have here the actual raw data, on the bottom left you have the isolated wobbles, so I apply the bandpass approach, and on the right are the spectra of those corresponding surfaces. You put in the positive and negative frequencies here just so that you can see the symmetry of it. But because we are measuring our vessel position and our vessel orientation the whole time, we know the period of these wobbles. We have a fairly good idea of them. And if we can use that to constrain a bandpass filter, we can probably create a more robust surface estimation procedure. And this is something I'd like to actually investigate for the thesis. So this is pretty much one of the first big proposals going on in the future. I just wanted to show what the quadratic surface would do in this situation. And if you have a fairly long quadratic surface, the spectrum doesn't change very much because what you're doing is you're really doing a very low frequency high pass filter. So the actual change in spectrum is tiny little thing you're kind of removing in there. But what you're seeing is you're overfitting the peaks, underfitting the troughs, and you are not accounting for the spike at all. So these get into the risk estimation, and they kind of make those estimates wobble, more wobbles. So this is just a quick analysis of the three results. So this is the true error, because simulation, I know what it is. On the right, this is the bandpass filter. On the left is the quadratic filter, which is similar to a Savitsky-Golay filter. And again, you just see that spike kind of not getting accounted for, but whereas the bandpass does kind of account for it. So back to the actual data, right? Back to risk itself. And what we have is applying that better set of parameters. So after I've applied my automatic filtering to the regions, you see that the data does get a bit nicer. So you go from this, look at the wobbles here, bit nicer, right? This is on one line of data, and what we figured out from my master's was because there's a lot of correlations going on, there's a lot of complications within the model, the assumptions can break down for a variety of reasons. It's not just is there motion or is there rough sea floor, but it's also how is that motion distributed through the motion parameter space, because we want to get a broad sampling of variation to really discriminate these parameters because they're all correlated, which, as I mentioned at the very beginning, is why we're doing a nonlinear optimization scheme. So we don't get a perfect solution even after removing some of the seafloor, but what we do have is a lot of data, right? So the Pisquatica, this is Daniel right here, helped me collect this data actually. Well, we're very familiar with seeing this sort of stuff, right? You have a lot of nice smooth seafloor, but there is actual geomorphology, geology around there. And this is 30 lines, this is 36. What I just showed you is one, right? So there's no shortage of data for analysis because, again, I don't need weird combinations of overlap. I can just throw in all the data we have, and once the majority of the assumptions, which are the main ones, are just do you have a smooth seafloor and do you have motion. Once those are maintained for the majority of the data, we should be able to asymptotically converge on the true calibration parameter. So just looking in at what we have here, this little zoom, this is actually some of the best data you can get. This is 100% overlap. We went out there, we wanted to really get a good look at what was happening here for some other thesis research projects. And although we do have a lot of overlaps, I've forced 6 integration errors in here. They're not massive errors. I put half a meter of lever arm errors in there, put 10 milliseconds of latency. So we do have all 6 simultaneously in there. I did put them in. And what ends up happening is you still have wobble. So we want to calibrate this data, but because it's numerically intensive, we don't want to calibrate all. So I applied the automatic filtering approach, and what you can see is, here's the bedrock that we don't want. Of course, we don't want any of these sections. The automatic method does pick up most of these fairly well, and which is odd is it kind of picks up something happening here. I would like to talk about with John what that might be. It might be some sort of current running along the seafloor, making things a bit rougher. But throw that out just for good nature, why not? But we go from about 1,500 windows down to half, which we're gonna really throw into risk. So we're just using the best data that we can in an effort to make this method closer towards real-time implementation. Now, let's make a closer look, a quantitative look at those 6 parameters and their time series of them. So we have surface sound speed at the top, latency, this is going through time, this is for one line, motion scaling, heading misalignment, X lever arm, Y lever arm. And as you saw earlier in some of the figures, we have just non-stationarity, so non-consistent estimates of these parameters. And we kind of want to know why and also how to fix it. So these are a bunch of local estimates. I take the mean of these local estimates, and that's what you're seeing up here, and that's the calibration parameter. So after one line, we have a calibration parameter. What I should say is I actually forced, as I said, half a meter of lever arms into the analysis. And the lever arms are kind of the ones that are the hardest to home in on, interestingly. But we are off by more than 10% here after one line, right? But we're not doing one line, we're doing multiple lines. So let me see here. I think I have 5 lines after this. Give it a little second to load. And you see the noise in the data, right? Some regions just aren't ideal for risk. But the thing that immediately stands out to me is that they seem to be bounding some value. They seem to be oscillating around something, and that something should be the true calibration parameter. So we've homed in now to 52 centimeters, so, much less than 10% error, 5%, maybe a little bit about 5% error after 5 lines. And the thing to notice is, okay, I forced a half meter error in here, but there could be a little bit of error already existing in the system. So we don't exactly know what the true value should be. We just kind of know it should be around half a meter. And the way that I would say that we've converged on a solution is that as you add more data to the analysis, the mean does not really change. So going from 5 lines to 10 lines, let it load. We have a change of 1 centimeter in the lever arm estimates. So we are kind of, I would say by 5 lines, we have sort of converged to a parameter that would be suitable for calibration. But because I have all the data, I just kind of ran it through 1520 just to see what would happen as we did an asymptotic analysis. And I was fairly satisfied after about 5 lines that I could get a calibration parameter. Now the thing is, when I apply the automated filtering, that noise in the time series goes away a lot. So the data becomes a lot cleaner in general. And this is one of the things that would hasten convergence, not only computationally, because you're analyzing less data, but also statistically, because your variations in your estimates is lower, so your confidence increases, and your threshold for being able to say when you actually have converged on a solution should occur quicker if you're going to do this in an automated fashion. So after doing all 36 lines, I kind of did overkill there. We went from the set of before surface to this after surface, and we get rid of a lot of the errors, right? There is a little bit of hint of some sort of wobbly stuff going on there, and one of the potentials for this is I only calibrate for the 6 parameters that I put into the model. There's a whole bunch of other systematic errors that could occur. For example, you have imperfect water column modeling. So you go over an interface between fresh and salt water, and that interface is shearing. For example, at a river mouth, you get some weird turbulence. We don't account for that in our ray tracing routines. So these sort of errors propagate to the seafloor in a high frequency nature that my wobbles will try to fit somewhat. So because of these other potential source of errors, and that was actually what was happening today, we were constantly, this is right at the mouth of the Piscataqua River, and right about here there was a tidal front that was slowly varying through time because it took 8 hours to survey. So we were constantly just going over a surface sound speed variation right here at the top, and this kind of made a time dependency occur in the surface sound speed error. So we never really homed in on a perfect surface sound speed calibration here, but it would actually cause some of the other errors to also diverge a little bit. So we made the data a lot better. It's still not a lot nicer for any application if you're going from this to this for classifying or just for providing to any consumer. This is a much better product in general. But there was room for improvement here. And not only room for improvement in better estimation, but how quickly can I do it? Because if we do have sort of time varying surface sound speed, but I could lock into the estimate in half a line instead of using 5 lines, then I could have a very powerful and accurate estimation tool consistently, even in the presence of some of these oceanographic issues. So what I want to do is look at the distributions of these time series as we get more and more data. So this is, again, the 6 parameters. And at the top, we have the unfiltered versions, and at the bottom, we have the filtered versions. So if I'm going to use the mean of these time series as my calibration parameter, I want the distribution to be somewhat normal. If you don't have a normal distribution and you're taking the average of that to represent the true value, you're going to get skewed to statistics, right? And that's what would happen if you were to use the filtered data set after 1 line. These aren't really normal distributions by any sense, especially this. And although we do remove a lot of the noise, we remove some of the good data too. And because there is some noise remaining here, and there's less redundancy, these distributions are actually heavily affected by this noise. So I want to wait until we do have something of resembling a normal distribution before I say, okay, this is the true value here, the mean is the true value for calibration. So after 5 lines, you see normal distribution starting to pop up. There is a bit of a bimodal distribution that Wiley-Brown. This was a seafloor dependence, it seemed to be, as we move along back and forth. Every time we alternate, we kind of get one side of the true value. But again, asymptotically, if you consistently go bimodal, the mean of that should be the true calibration parameter. So we don't have normal distributions yet here at the bottom, but at the top we do, but we're most importantly getting rid of a lot of the outliers. So we have a lot of the noise getting reduced, but I would say again, by 5-10 lines, we're fairly good. But we just want to make it a bit better. And again, overkill, I did all 20 lines here. And you've got really nice distribution. So the method does certainly work. After 20, 30 lines, the more data you put in, it shows that there is, in a law of large numbers sort of a concept that we do home in on the true solution. I just want to be able to do it quicker. So what I did was I kind of leveraged some of the machine learning optimization research that's been going on for the last decade. Well, it's been on for a lot longer than that, but blowing up a lot in the last decade. And here's that parabola I was showing you guys earlier that we're going to try to close to the bottom of, right? This parabola isn't as nice as the first one I showed you. It's not just a perfect bowl. It's a little stretched out. It's actually a multivariate Gaussian. But looking from the top, what we have here is the gradient descent method, so just going straight downhill, versus ADAM, which is adaptive moment estimation, which uses the history, so the momentum of the previous estimates to go down that hill. And because we're using that history, we have a much more stable trajectory. And that's the important thing here, because we've noticed that our estimates are subjected to noise. Noise is just imperfect modeling. And because of that, we kind of jump around in parameter space where we shouldn't be. We want to stick in the true distribution parameter mean. And when we do hit those noisy regions where our assumptions break down, we want the trajectory or history of our previous estimates to say, no, that doesn't quite look right, kind of just skim over this region of parameter space. So I'm going to leverage this technique and kind of put a little flavoring of my own on it to really make a better optimization technique. Because currently what I use is just Gauss-Newton, which is basic nonlinear least squares, but there are more robust means of estimation out there. So click, and this is my little flavor that I'm going to approach to ADAM. So remember those 6, walking around time series? Here's an analogy of it. right? So the true value is this 1 through time, and then you hit some bedrock and you've got a jump in your solutions. So this is a 10% error because we are just taking the average of all of these. But if I was to then consider momentum and shuffle the data, so a deck of cards, you're going to throw that bad area throughout the data set. If you can then apply momentum to the shuffled data, what happens is you kind of just roll through these outliers. So although we're going to try and detect a lot of these bad regions, the ones that go undetected should become less of an issue by applying this momentum. So this is the second proposition that I'm making for my thesis, is to actually implement this adaptive moment estimation into the solution of risk. And the final thing that I really want to get at is, okay, we can make it statistically faster, so we need less data to converge, but what if we can make every solution faster? And remember, at the very beginning, I was mentioning this hyperbolic intersection we have to do. It takes a couple of iterations, it's numerical. What happens is you have this hyperbola, you intersect them, and then you estimate the time that it takes to get to that spot, and does that match your measured two-way travel time? If it doesn't, you then have to adjust this focal plane, and you have like a nested conversion scheme. And because it's nested, it takes multiple iterations. So the hyperbolic intersection can take 3 iterations, then the focal adjustment can take 3, so it's like 3 squared, 9 iterations to solve. What I want to do is kind of explain how we can make that better. Now, the current method accounts for refraction. So what it does is, say we have a layer here, so let's just do a 2-layer model. Say we have a layer here that has a very different sound speed than the top surface. That hyperbola does bend as you go through that water column, right? So this is the conic section there at that interface, and the hyperbolas themselves move through space. And importantly, they actually stretch too, because the surface sound speed variation means your distance and time correspondence scales as well. Now, what we've come up with is we can solve for the same azimuth of intersection by ignoring this refraction. So where these hyperbolas intersect, if you account for refraction, which is down here, versus where they intersect when you don't account for refraction, still gives you the same source azimuth, so the same exit from the actual transmitter and receiver. So we can much more efficiently home in on these two values, because that's what this intersection model is solving for. The intersection model is not solving for where does it actually hit the sea floor, but it's solving for where do they correspond, the transmit and receive cones of sound, where do they correspond, and what was the launch angles and receive angles that they came in and went out on. And also we do have to separate the two-way travel time into two one-way travel times. But the big thing here is figuring out what these azimuths are. So the way that John actually posed this to me, which made a whole lot of sense, is think of a straw in a glass, right? So we have two straws here going into a glass, and this is the inverse of that problem. The straws in the glass, they actually hit in that glass in a straight line. They don't bend, but you look out from through the glass and they meet in a different position, right? This is taking that and flipping it on its head. This is doing the inverse of that. This is saying, okay, those straws, in this case of beam vectors, do bend, they do hit in a different position, but if we ignore that bending, we can still find out the original azimuth of the launch and direct and receive angle. And this is a much quicker approach because we don't have to calculate sound speed profiles as we iterate through depth. We don't have to rotate from this reference frame that we actually do the solution in into the sound speed profiles reference frame. So it's a much faster solution. I have a tested implementation of it. And we can also solve this directly in 3 dimensions. So it's a 3-dimensional problem with a 3-dimensional solution instead of having to iteratively solve the x, y, and then the z. We can solve all 3 at the same time because it's closed form. It's just intersection of vectors. So This is the third thing that I would like to propose for my thesis. And just, to take a closer look at what's happening in this, straw in the glass problem. You have that launch angle. This is what we really want. The reality of the signal is it comes down here, and this is where it intersects on the seafloor. But this is where we assume it is by ignoring this different sound speed in this layer. And the thing is, you still get that correct launch aspect. And from the front view, it's the same thing again. You have that launch angle. There's refraction there. And I just want to show from the top here why we have to do this hyperbola. Looking at it now, I need some better lighting. But if you don't account for the offset between these transmitters, so methods exist such as the concentric intersection approach, where you assume these transmitters are co-located, and there's a closed form solution. It's very fast. But the thing is, if you don't account for the offset in these parameters, you intersect these hyperbolas in vastly different locations. And because of that, you just get your azimuths incorrect, and then you don't distribute your two one-way travel times, so the transmit travel time and the receive travel time, correctly, and you don't have a high fidelity solution. So to be able to match Konsberg solutions, because the only way that we can calibrate Konsberg's data is to match their results, is we had to go to this high fidelity approach where you have a more accurate recreation of the physics of the system. So I think that's pretty much it for me for time. So just in summary, what I wanted to do was utilize and test the ability for a more robust seafloor model. So using a bandpass filtering approach instead of a high-pass filtering approach, which is what a quadratic surface would do. I wanted to implement atom optimization schemes for a more robust solution in general, something to just not really track those bad regions as well, bad for risk. And then use a faster cone intersection model just to speed up the whole process. And all of this is in an effort to hasten the workflow towards a real-time implementation of this routine. So that is it for me. And if there are any questions, I'd be happy to take them.